So talking about thermal expansion, this has to do with the fact that as a material absorbs energy, there are lattice vibrations, and those lattice vibrations will also correspond to the material having a certain displacement from its lowest energy minimum. So going back again to our picture of bonding, in which we have some type of energy well like this, that R. We have atoms that are connected by some imaginary spring, size R. At the bottom here, that's our R0. That is the optimal separation. So you can imagine, though, that as we start absorbing energy in the form of thermal expansions, we're going to oscillate between temperatures, or between displacements, which will increase the energy, and that goes into heat capacity. And as we increase this more, there's an asymmetry, right? So now the average displacement is no longer R0, but now it's actually a little bit over here. So at larger displacements, like this, the average displacement is shifted a little bit to a larger R0. And in fact, as we go along here, we have a net displacement due to the anharmonicity of the energy well. So down here at the bottom, this is approximately harmonic, right? We can just treat it as r cubed, or sorry, r squared. But up here, at higher or at larger energies, it becomes anharmonic. So that is the origin of the origin of thermal expansion. Now, talking about thermal expansion, we can express it in terms of the change in the lengths. So this is from some linear L0, increase the temperature, and now it's a longer wire. The change, or the fractional change, L Tf minus T0. That is our linear coefficient of thermal expansion. Alternatively, we could also talk about a volumetric coefficient of thermal expansion, and talk about the fractional change in the volume. V delta T. So now that, with a alpha sub V, is the volumetric coefficient of thermal expansion. Because the degree of change in length or volume with temperature depends on the anharmonicity of this energy well. You can certainly imagine that something with a large, flat, fairly anharmonic well will be very different from, for example, something with a sharp cusp, right? Something with a sharp cusp like this, where you only start to see that change when you get up to relatively high temperatures, large changes in energy. Whereas here, even a low change in energy, you start to see displacement. And this is why ceramics typically have a smaller coefficient of thermal expansion. So ceramics their alpha L is typically around 1 to 15 times 10 to the minus 6. In contrast, metals, alpha L is typically around 5 to 20 times 10 to the minus 6. I should put the units in here too. The units have to be, that's a fraction, that's temperature, so this must be 1 over temperature. This is 1 over degrees Celsius. Over degrees Celsius. And then polymers, which have a much wider, more open cusp here. Typically ranging from, say, 50 to 500 times 10 to the minus 6 inverse degrees Celsius. So when you're thinking about materials, you can think largely about how they behave in terms of this pairwise bonding. It's not, necessarily a very sophisticated model for material science, but it's actually fairly accurate and useful for understanding the general trends that you'll be seeing.